in this example, we'll verify Stokes' theorem for the vector field F equals 2yzi minus y squared j plus xyk. That's depicted over here. And then our surface, so we'll do this over our surface will be the cone z squared equals x squared plus y squared with z between 0 and 2. So the first step is to find the curl of this vector field. Okay, so curl F is del by del x, del by del y, del by del z, ijk, now 2yz negative y squared xy. And so that is, let's see, so for I we've got x and then 0, so xi. For j we've got 2y minus y, so plus yj. And for k we've got, so 0, and then this is minus 2zk. So here is the rotor for that curl. All right, the next step is we want to parameterize this surface. So we'll parameterize this by C of r theta is r cos theta I plus r sine theta j plus rk with r between 0 and 2, since that's our z range, and theta, of course, between 0 and 2 pi. Then this gives that okay, so CR cross C theta is, okay, determinant, so this will be cos theta sine theta 1, and the negative r sine theta r cos theta 0, which is so negative r cos theta I. This is right, minus r sine theta j, and then plus r k. Now, we recall that our formula for, so when we have a parametric surface, we found that curl of f dot normal d sigma was equal to curl of f dot cr cross c theta dr d theta. So that will give us, so we only need this now. So we just need these two things. So this will be, so x is r cos theta I plus r sine theta j, and then minus 2z, so that'll be minus 2rk. We dot that with this, so negative r cos theta I minus r sine theta j plus rk dr d theta. So this gives us, these two give us a negative r squared. This gives us a negative 2r squared. So this is negative 3r squared dr d theta. So now we can evaluate our integral. Integral over S of curl of f is integral 0 to 2 pi, 0 to 2, negative 3r squared dr d theta. So this integrates to negative r cubed, so that'll give us a negative 8, and then times 2 pi. So we get negative 16 pi for the surface integral. Okay, next let's tackle the surface, the curve side. So we'll parameterize the boundary of the cone by r of t is, so this is where the circle has radius 2. So 2 cos ti plus 2 sine tj plus 2k, and then 0 t between 0 and 2 pi. Note, so we need to make the orientations match up. So the way we parameterize the cone, CR cross C theta, the k component of this was just r. This is greater than 0. So this is telling us that the normal vector of the cone, as we've chosen it, is pointing upwards and inwards. And so therefore our orientation of the curve, the circle should be oriented counterclockwise. And this is a counterclockwise orientation of the circle. So this is just to check that our parameterization is done with the correct orientation. All right, so now we can integrate. So integral CF dot dr, this is integral 0 to 2 pi. Okay, so now f is 2yz, so that'll be 8 sine ti minus y squared j, so minus 4 sine squared tj, and then plus xyk, so plus 4 cos t sine tk. We dot that with dr, which is negative 2 sine ti plus 2 cos tj, and then no k component, dt. So that dot product is well, first let's pull a negative 8 out of everything. So negative 8 integral 0 to 2 pi. So now this will be 2 sine squared t minus sine squared t cos t, and then this k term goes away, dt. Now we could integrate, so we could split this into two parts, and then we could integrate this by doing like a substitution. But actually we can see that this will integrate to 0 just by oddness, or that we're sort of integrating this over, like if we go over the circle, we have like the negative cos values here and the positive cos values here, but the sine squared is going to be the same. So that will integrate to 0 anyway. So then we just need to integrate. So this becomes negative 16 times whatever the integral of sine squared is. And by, I think it's number 65 in the table of integrals, back of our book, we have t over 2. Actually, let me check this. Yeah, t over 2 minus sine 2t over 4 at 2 pi and at 0. And that sign isn't going to contribute anything. So this again is negative 16 pi, as it should be. We can also try this for a different surface having the same boundary curve. So let's also consider, instead of the cone, just the disk D. So this will be parameterized by, let me call this P of, P of r theta will be r cos theta I plus r sine theta j plus 2k. So r again goes from like this. So now this gives p r cross p theta is cos theta sine theta, and now 0, and negative r sine theta r cos theta 0 I jk. Well, I guess in this case we actually could have just sort of observed by looking at it that the unit normal is, that the normal of this is going to be straight up, but so this, the normal here is just rk. And so now the integral over d of f, curl f dot normal d sigma, this is going to be the integral of so 0 to 2 pi, 0 to 2. So we still have the curl of f will be r cos theta I plus r sine theta j, and now minus 4k. But then when we dot that, we dot that with 4k is the cross product here. So, and then dr d theta. So our integral is even easier this time around. It wasn't too bad with sort of the best, sort of from best to worst integral was sort of, this is the nicest, cone was the second nicest, and then the circle was actually the worst. But anyway, so this integral becomes integral 0 to 2 pi, integral 0 to 2 of now minus 4 r dr d theta. So this, we get negative 2 out. This will be negative 4 pi times, and then this will have a 2r left over, so an r squared times 4. So yet again, we get negative 16 pi, as we should.